Hello, so let's continue now with the systems of linear equations that we were talking about in the previous video. So if you recall, we have products uppercase n1, n2 all the way up to nn, and then resources r1 to rm and then to produce a unit of product nj, we said aij units of ri are needed, and then if available units of the resource ri are bi and units of this product nj produced as xj, we wrote this set or system of linear equations. So there are basically m equations here, one equation per resource, okay, and then we said the optimal production plan has to satisfy these equations, right. So let's look at some more concrete examples of the system of linear equations. So this is example 2.2 in the book, and it goes like x1 plus x2 plus x3 equals 3. So there are, it looks like there are, in this case drawing analogy to these, there are three products, right. Just looking at this one, there are only x1, x2, x3, right, and then the next equation is x1 minus x2 plus 2x3 equals 2, and then 2x1 plus 3x3 equals 1. Okay, so these three equations are given, they are of this form, the system of linear equations. Now if we look at this, we can interpret this in this kind of context, since we have x1, x2, x3 and that's about it. We can think, okay, so there are three products and how many resources are there, and since we have three equations, we may think that there are three resources, right, just to draw the analogy with the text, right. But if we just observe this, so if I call this as equation 1, this as equation 2 and this as equation 3, what happens is if I add this equation 1 and equation 2, right, so I'm going to add, so equation 1 and equation 2, right. So what do we get? So we get 2x1, right, and then this is plus x2 minus x2, these two cancel, and then we get 3x3, and that's going to be again equal to 5, right. So now if you see here, this contradicts equation 3, right, because here 2x plus 1 3x3 equal to 5, here 2x1 plus 3x3 equal to 1, and these two are contradicts or conflicts, right. We can say rather than contradicts, I think we contradicts or conflicts, right. So conflicts 3, so no solution, right. So this is a case where you cannot solve the system of linear equations, right. Now we'll move on to another example. So now we have x1 plus x2, x1 plus x2 plus x3 equal to 3, x1 minus x2 plus 2x3 equals 2, and x2 plus x3 equal to 2, right. Now in this case, so if we use, so this one, let me call it now, in this case this is equation 1, equation 2, equation 3. So if I do equation 1 minus equation 3, right? So I'm taking the first equation x1 and there is no x1, so that remains. So we get an x1, and then the x2 and x2 cancel, and x3 and x3 cancel, and you essentially get x1 and then 0 x2 0 x3 equal to 1, right? So x1 equals 1, and since x1 equals 1, right, then what we do is basically we can add equations, let's say 1 and 2, right? So if we add equations 1 and 2, we get 2x1, then the x2 cancel, plus 3x3 equals 5, right? And then I can substitute the value of x1 back here, so this becomes 2 plus 3x3 equal to 5, and then subtracting 2 from both sides, we get 3x3 equal to 3, thus x3 equal to 1, right? So x1 is 1, x3 is 1, and if x3 is 1, again we can substitute the value back in 3, so from 3 we get x2 plus x3, so I'll use this value of 1 equal to 2, so x2 equal to 1 also, right? So in this case the solution is unique, right? And what is the solution? The solution is we saw x1 equal to 1, so 1, x2 equal to 1, and x3 equal to 1, right? So the solution is unique, right? The previous example that we saw, we found that it can have no solutions, right? And again we can always take this 1 1 1, plug it back into these equations and check whether it works, right? So if x1 1 1 1, 1 plus 1 plus 1 is 3, that's correct, and then we have 1 minus 1 which cancels, and then 2 times 1 is 2, that works, and 1 plus 1 equal to 2, so all of them work, right? So this works. And then as third example, let's consider this other equation. So the third equation is, or third system of linear equations is x1 plus x2 plus x3 equals 3. So that's the first equation. Second equation is x1 minus x2 plus 2x3 equals 2. That's the second equation. Third equation is 2x1 plus 3x3 equals 5. Okay. Now in this case, if we add up equations 1 and 2, we get, so I am taking equations 1, these first two equations, we add them up, so we get 2x1, and then the x2's cancel, and then we get 3x3 equals 5, right? So this is same as 3. So 3 is redundant, right? So we don't need 3, right? So what we can do is simply express this x1 and x2 in terms of x3. So let's see how we can do that, right? So from this, or from which is same as 3, so we get, if we go here, we get 2x1 equal to 5 minus 3x3, or in other words x1 equal to 5 by 2 minus 3 by 2 x3. Okay, and then we take this and substitute back here, so that will give us substituting x1 in 1, we get 5 by 2 minus 3 by 2 x3 plus x2 plus x3 equals 3, right? And then we can simplify this to be 5 by 2 and then minus 3 by 2 x3 and 1 x3, that gives me minus half x3 plus x2 equals 3, or this means x2 equals 3 minus 5 by 2 plus half x3, and this means this x2 equals half x3, and then here we are going to have this is 6 by 2, right? 3 is 6 by 2, 6 by 2 minus 5 by 2 is 1 by 2, so plus half, right? So in general, this x3 becomes a free variable, right? So I'm just going to continue here since it's easy. I don't need to use a new sheet and lose track and copy everything again. So I'm continuing here, right? So x3 is a free variable, so we can set it to any a belonging to R, right? So the solution set is, I'll take this x1, so that's going to be 5 by 2 minus 3 by 2 x3, but we will write 3 by 2a, correct? And then this guy is just half plus half a, right? Or half a plus half, same thing, and a, right? A is the third dimension, which is x3, right? And then a is in the set of real numbers. So any possible value of a is going to work, and this is the case where we have infinitely many solutions. Okay, so the three different cases, right? So let me again reiterate what we learned. So let me go back to the first one that we did. In this case, no solution, because when we added up equations 1 and 2, the constant term became 5, right? The left hand side 2x1 plus 3x3 same here, and then there is a conflict between these two. So there is no solution, there is no x1, x2, x3 that can solve all these three equations, that can fit into all these three equations, right? So that's no solution case. And then there is this unique solution case that we went through, which is this one, where we just had only one solution, 1 1 1, and then that fit in this equation. So there is a value, a unique value, or a unique x that's in R3, right, which is x1, x2, x3. There is a unique x in R3 that satisfies this system of linear equations, these three together, right? And then here we saw for this system of linear equations, these three equations, right, that we have infinitely many solutions of the form. This is the form of the solutions, right? Infinitely many again doesn't mean all possible values of R3 can solve this, right? Infinitely many only means this a is the only free variable, and the solution has to be of this form. It cannot be anything in R3, right? So that's very important, right? Infinitely many does not mean the whole of R3. Infinitely many only means solutions of this form. For example, I can take a equal to 0, a equal to 1, 2, whatever, like even any real number, 0.5, 0.1, 0.01, anything, and then I can substitute the value for a here. That will be a solution to this system of linear equations. Okay. So moving on, let's see what the authors are talking about next. In general, for a real valued system of linear equations, we obtain either no exactly one or infinitely many solutions. Okay, so that's what we saw. Then linear regression in chapter 9, solves a version of example 2.1 when we cannot solve the system of linear equations. Okay, so linear regression is you cannot really solve it, then what do you do with it? That's what linear regression is about. Okay, and then the authors go on to remark that geometric interpretation of systems of linear equations, right? In a system of linear equations with two variables x1 comma x2, each linear equation defines a line on the x1 x2 plane. Since a solution to a system of linear equations must satisfy all equations simultaneously, the solution set is the intersection of these lines, right? The intersection set can be a line if the linear equations describe the same line, a point, in which case you have a unique solution, or empty when the lines are parallel, right? So that's illustrated with an example like this. So the let's take, so we have x2 dimension here, and this is an R2, right? So this is the x1 dimension, and there is one line like this, and then another line like this, and then this is the solution, right? And this one is 4x1 plus 4x2 equals 5, and this line is 2x1 minus 4x2 equals 1, right? And then we know from high school level math, we can solve these. They are called simultaneous equations, which is same as the system of linear equations, right? And then what is the solution? We can solve for it, multiply this times 2 and subtract. So if we do that, then we get, so let me write that down. So we have, so let me call this as equation 1 again, and then this as equation 2, right? So equation 1 is 4 times x1 plus 4 times x2 equals 5, and then 2 times equation 2 is going to be 4 times x1 minus 8 times x2 equals 2, right? So if we subtract these two, we get 12 times x2 equal to 3, right? So this is again equation 1. If I call this equation 3, this is equation 1 minus equation 3. Okay, so that's what this is. So we get x2 equal to 1 by 4, right? x2 equal to 3 by 12, which is same as 1 by 4. Okay, and I can take this x2 value, substitute it back here. So subbing in 1, we get 4x1 plus 4 times 1 by 4 is 1 equals 5. So x1 equals 5 minus 1 by 4, which is 4 by 4, which is 1, right? So 1 comma 1 by 4 is the unique solution, right? In this case, right? So this is the geometric interpretation where two lines are meeting. In the previous example, the no solution case is when two lines are parallel, they will never intersect, right? In 2 dimensions. So that means they have no solution. And then the infinitely many solution is the two lines are the same, right? Which means you have two lines, one lying on another, then all points on the line are solutions, right? Similarly, if you have it in the 3 dimensions, right? So you can imagine, like, so let's take this paper as one plane, and then I have another plane like this, right? And then another plane like this. Okay, so I'm just using my 2 hands for 2 other planes, right? In this case, so this point which lies on this but then also lies on this plane and this plane, that point is going to be the solution, right? In which case that's a unique solution. But you can also imagine the 3 planes, like, so this is one plane, and then second plane is like this, third plane is like this, right? So in which case you can see right there that line, all the points on that line are going to satisfy, right? So all 3 equations, right? That's the second case. And then if, for example, a plane is 2 planes are parallel, then you're not going to have any solution, right? Or all three planes are parallel, again you won't have any solution, right? And when two planes are parallel and the third one cuts them, right, you don't have any solution either, right? So that's what the authors are talking about next. Similarly, for three variables, each linear equation determines a plane in three-dimensional space. When we intersect these planes, that is, satisfy all linear equations at the same time, we can obtain a solution set that is a plane, a line, a point, or empty. Okay, so one of the things that maybe I didn't talk about is so we saw a line being an answer. That happens when these two planes are like this, right? And then I'm assuming the paper as one of the planes, it's easy for me. And then a point also when it's like that, right? And then empty is when all the three planes are like this, right? The paper and then my two hands are the planes and they don't ever intersect, that's fine. So when can the solution be a plane? That is something that I need to think about. Let me pause the video here because and then I'll continue in the next lecture.